All right, my friends, here's a little help video for number 19 on section 11.5. So here's the situation. They gave you the graph of f of x equals negative 1/3 x plus 4. Oh boy. There we go. Something like that, except use your imagination, but that looks super great. So they're basically wanting you to approximate the area of the shaded region, which is hilarious because this is a triangle and we could just do area equals 1/2 base times height and get it exactly using basic geometry, but that's okay. It's good practice with the concept, right? So they've given you f of x equals negative 1/3 x plus 4, basically on the interval from 0 to 12. And they're asking you to approximate the area of the bounded region using let's see. So this table has us kind of doing 4 different math problems because they want you to approximate the area of the region using 4 rectangles, then 8, then 20, and then 50. Like so, okay. So you can kind of imagine, like here would be your subintervals for 4, and then here would be your subintervals for 8, and then you'd have 20 of them, I guess, for 20, and etc. So by the time you're doing 50 rectangles, you probably have a decent approximation for this lovely problem that you could have done geometry on, but anyway, so what I'm going to do here is demonstrate something that I demonstrated in an example, I think in 11.5 part 1, where you don't treat it like 4 different problems because that is more headache than any of us need. And so instead you can just generalize the situation. And then basically just do it in terms of n, where n is just the number of rectangles. And it is kind of redundant for me to write this again, because if you look at the table, that is what they're saying n is in the first place. But if n is the number of rectangles and you just leave it kind of variable like that, then when we're all done, we'll get a little formula, and then you can just pop in 4, 8, 20, and 50, and boom, have it. So if n is the number of rectangles, then let's think about how wide would each one be. So the width of each rectangle would be, well, you have 12 units altogether and n rectangles, and they're all supposed to be the same width at the bottom. So you take the width available and divide by the number of rectangles, and that's how wide each one would be. So now you have the width, and now it's just a matter of adding up all of the areas. And this is not an exact area problem. There will be a little bit of error, even with 50 rectangles. So what I'm going to do is I'm going to say area is approximately, and then you'll notice it's just like finding exact area. You just won't have the limit as n goes to infinity in front. So area would be approximately. I'm going to go ahead and just say the sum as I goes from 1 to n of, and then in here you're going to see base times height type stuff. Well, the base of every rectangle is 12 over n, and then you want a height expression for the ith rectangle. So if you think about, well, you start at 0 and you would have bumped over 1 width and plugged that in to get the height of the first rectangle, and then you would have bumped over 2 widths, so I'll just say 12 over n times 2 to get the height of the second one, and then 3 widths, etc. So basically the number of 12 over n's you've bumped over matches the number of rectangle you're on. So to get the height of any ith rectangle, you do f of 12 over n times I to get the height of any ith rectangle, like that. So here's your setup, and then now what I'm going to do is just mention that since in this problem f of x is defined as negative 1/3 x plus 4. F of 12, I'm going to call this 12I over n, would be negative 1/3 times 12I over n plus 4. And then you could cancel with the 3 and the 12, and you'd have negative 4I over n plus 4. And now we can take this and then plug it in for the height piece right here. So you'd have that the area is approximately the sum as I goes from 1 to n of 12 over n times negative 4I over n plus 4. So I just replaced f of 12 over n times I with this expression. So in previous videos, I demonstrated factoring this out first and then distributing sigma. For this particular problem, I actually like distributing that first. So I'd say the area is approximately the sum as I goes from 1 to n, and then if you distribute that in, you get negative 48I over n squared plus 48 over n, like so. Now distributing sigma over the addition, and I'm going to go ahead and skip a step because I'm to the point with this where I feel like you guys can take it. So I'm going to distribute sigma over addition, and at the same time I'm going to factor out the constants in front of each statement. So remember, as far as sigma is concerned, I is the variable and the other things are constant as far as sigma is concerned. So I can basically write it as negative 48 over n squared times the sum as I goes from 1 to n of I. And then plus, and this is all a constant as far as sigma is concerned, so I think I'll just go ahead and leave it in there. If you factored it out front, you'd have to leave a 1 in there, but I think I'll just leave it in there. Okay, so now getting to the point where you have this all in terms of n, so we can replace this with its appropriate formula, which I hope you have memorized for your well-being, math well-being. So you'd have n times n plus 1 over 2, replacing that entire sigma statement. And then here, this 48 over n is a constant as far as sigma is concerned, so you're just going to multiply your upper bound times 48 over n, like so. Okay, so now let's cancel things down. For when things aren't going to infinity, I do like to simplify these things. So 48 and the 2 cancel. You'd be left with, I'll just write negative 24 there. This n can cancel with one of these, and so you'd be left with negative 24 times the quantity n plus 1 all over n. And then these n's, of course, cancel, and then you'd be left with plus, that was a weird way to write a plus anyway, plus 48. And so here we go. Here is a fairly simplified area expression for this region using n rectangles. So now what we can do is you can, if you want, you could just grab your calculator. I mean, this is something you could do without, but you know, by the time you're to this point in a problem like this, probably you'd want to be nice to yourself and just grab a calculator. So I'm going to enter this function rule in. I'm just using x's instead of n's. The calculator won't care what you call it. So I'm going to let this rule be y1, and then make sure you go to table set, which is the window button, or F2. So go to table set, and then make sure it's going to ask you for the independent and automatically calculate the dependent based on what you entered in for y just now. And then if you go to table, even if you have stuff in here already, you can just enter 4, 8, 20, 50 over whatever you have, and then it'll give you the area. So if we just used 4 rectangles, we would have gotten 18 square units for the approximation. If you use 8 rectangles, you would have gotten 21 square units. 20 rectangles, 22.8 square units, and then 50 rectangles, you would have gotten, let's see if this is, yeah, you would have gotten 23.52 square units. And I hope that makes sense to you here, because the more rectangles you crammed in, the more you'd reduce this area, or sorry, this error here. And then, you know, what would the exact area have been all along? It would have been 1/2 base is 12, height is 4, and so the exact area should have been 24, just based on basic geometry here. Anyway, don't be mad about that. This problem is just really to like help you get ready for finding exact area for things that you can't use geometry on. Anyway, so think of it as a practice. Anyway, I hope this helps everybody. I know these problems can be tough, and I hope it's a relief to see how you could generalize this into one problem and then use your formula to just fill out the table. If it did ask for exact area, you would just have a limit as n goes to infinity in front of each statement, and then you would have gotten that exactly 24 piece. The geometry says the answer should be anyway. All right, take care, everybody.